My brother Bill and I have been developing what we call HiPerSolar systems. They use a high-performance solar collector, some thermal storage, along with some type of wood burner. Our goal is to have them heat our homes without burning fossil fuels. Traditional solar hot water panels deliver only a few % of what we need and are too expensive to use for space heating. Our Hyper systems will be easy to make with only simple tools. The stack of mirror assemblies shown use simple extrusions and mirrors. We will add these to our first prototype when it's ready. Anyone who can use basic tools should be able to assemble all the components. Even though we have built the large solar equipment shown in the next few photos, we believe that these are now inappropriate. Remote, complex systems just don't pay for themselves. Our first Hyper system pictured here was built to work out issues with drives, tracking, and optics. By comparison, typical dish-shaped solar collectors that also achieve high performance use a single heavy post and gearbox assembly. All wind forces must pass through a very expensive knuckle joint and a single foundation. These use complex equations to follow the sun. They also use expensive sensors to aim the mirror array, as well as experts and a crane for installation. Hyper systems use a wide base of support and a few small foundations. Two lightweight drives with very high mechanical advantage spread wind forces over the wide base. The one pictured would provide all of my hot water and half of my space heating in Troy, New York. And the solar controller will learn the sun's motion by itself. One drive moves the collector east and west to adjust for the changing positions of the sun throughout each day. At night, the mirror array is parked upside down to protect the mirrors. In the morning, the mirror array faces east before sunrise. When the sun appears, the mirror array rotates 1 degree every 4 minutes, just like the Earth. It can rotate faster if it needs to stow before a storm. At sunset, the machine returns east before parking upside down. The other motions move the mirrors and receiver up and down to adjust for the changing positions of the sun between summer and winter. HiPerSolar systems can be erected by hand using a come-along or winch. Some controllers will use open source code so others can add code or change platforms. During the summer, when there is more energy available than winter, it can be used to recondition desiccants. Desiccant dryers can dehumidify basements or dry food, clothes, wood fuels, or other items. They should be simple to make and should do well using the high temperatures available from Hyper systems. Desiccants can also cool air. Oil production data makes it all too clear that we should be developing low-cost solar equipment. Early U.S. oil wells could produce 100 barrels of oil for each one used to develop the resource. 40 years ago, 30 barrels of oil were produced in the U.S. for each one expended. Economists generally believe that advanced economies unwind when that ratio drops below 12 to 1. Today in the U.S., the ratio is 11 to 1. For fracked oil and gas and tar sand oil, each one invested only delivers about 5 barrels. Yet we are not ready for an economy that lacks a steady supply of oil and gas. But typical solar equipment today is too expensive without subsidies. Our work now addresses costs that pivot on two things. With the least amount of inexpensive materials, harvest and use the most energy, and empower users to help make and set up the equipment. All designs will aim sharply at these two criteria. We hope to speed development by starting small. Maker movement should be able to help models progress into larger equipment. We work with two types of models, those that use physical parts and computer models. Both quickly illustrate important issues, whereas working on larger scale equipment takes far more time and resources. Previous models that helped us to where we are now are pictured. We already have working prototypes of our evolving design. We've completed structures, drives, mirror assemblies, and ways to superimpose mirror reflections into a receiver lined with tubing. What we do not have are friendly controllers that can run solar collectors for 30 years. Open source code working on low-cost platforms like Arduino, Raspberry Pi, BeagleBone Black, and PLCs are all appropriate. We are developing a tabletop model that others can use to prove their approach that we will verify. Each model features a small Fresnel lens, a PV panel with a battery and charge controller, and a gear motor for each drive. In addition, each model will include 2 pairs of limit switches, one for each of 2 motions, revolution counters and motors for daily and seasonal tracking, 2 sun intensity sensors for measuring the energy available from the whole sky and directly from the sun, 2 pairs of shadow band sensors used to orient the structure toward the sun, 2 sets of high temperature sensors used to center reflected energy on a target, a sensor for measuring the temperature of the target, and an interface with switches and connectors. These will make it easy to hook up and manually control operations and turn over controls to a candidate controller. We hope to trade these models for code on appropriate platforms. Tabletop models should encourage makers to develop friendly controllers. These friendly controllers should then excite folks to harvest their own energy. Friendly controllers will log performance and alert users when needed. Of course, controllers that operate models can also run larger equipment. While we work with controllers, we will also ascertain what size solar concentrator will be the most appropriate next step. We will analyze energy bills in use to determine appropriate sizes for larger equipment, investigate potential sites for solar resources, and look for partners who make parts or support systems. Less than 15% of the sunlight received by large desert solar project reaches the customer. 20% of the sunlight on rooftop hot water systems where we live is actually used. 80% of the sunlight shining on HiPer systems is available at high temperatures. HiPer systems can readily provide space heat and domestic hot water. It can also cook, dehumidify, dehydrate, and heat hot tubs, saunas, and swimming pools. Virtual models in SolidWorks determine the strength of components needed during high winds or snow loads. It also produces lists of parts, material weights, production and assembly techniques, and illustrations. This video is a brief introduction to what Bill and I are doing now, where we've been, and where we hope to go. We will produce more videos when we have more to share.